Okay, in this video we're going to talk about what we call special case triangles, and this correlates with section 9.2 in your textbook, so I've put 9.2 here, even though the assignment you're going to do today is a worksheet. Our learning target today is students will be able to, so I want you to first understand where they come from, these relationships, and then be able to apply the special relationships of the sides of two types of triangles. One is a 45, 45, 90 degree triangle, so that's the measure of their angles, 45 degrees, and a 90 degrees, so notice it's a right triangle. The other one is 30 degrees, 60 degrees, 90 degrees. So again, a right triangle where the other two angle measures are 30 and 60. So these are two triangles that we call special case triangles. Okay, I'm going to show you first where these relationships are going to come from. This allows us to identify the sides of the triangle without having to use the Pythagorean theorem every time. It's kind of a shortcut. Now, can I use the Pythagorean theorem each time? Yes, if I'm given two of the other sides. But again, this relationship, and when we do some practice ACT questions in the future, we'll kind of use those. So let's start with the relationship here first that comes from a square. Now, I tried to draw these as squares. You're going to assume they're squares. I'll put these on there so we can assume that. So here's a square, and here's another square. And I'm just going to give you a couple different lengths, and then I'm going to calculate using the Pythagorean theorem the length of the diagonal of the square. And we'll notice when we create a diagonal, it creates two triangles. So here first we have this square here, and let's say that this is going to be 5 centimeters across, which means this is 5 centimeters and then 5 centimeters all the way around. Let's just make this one 10 centimeters to be easy here. And let's make this one over here 2 centimeters, even though definitely not drawn to scale. Again, if I draw a diagonal in here, I'm going to use my straight edge tool and hope I make it correctly here. Okay, pretty good. The diagonal here, when I draw that in, allows me to create, again, two triangles. So I'm going to look at just this top triangle. And remember that the diagonal of a square actually bisects the angles. So if this was a 90-degree angle here in my square, this was also a 90-degree angle. When I draw that diagonal, it's going to cut that 90-degree angle in half. This becomes a 45-degree angle. This one's also a 45-degree angle, given that that was a square. Notice now, this is one of those special case triangles. This is what we call 45, 45, 90. It's just a half of a square. Now, notice in a 45, 45, 90, the first thing we can always say is that their legs are the same exact length. Because it's a half of a square, whenever I see 45 degrees in one of the corners, I know the other one's 45 if it's a right triangle, and I can just immediately assume that these two legs are going to be the same length. Okay, now how does that relate to its hypotenuse, or the long leg of this triangle here? Let's go ahead and calculate. So if I wanted to figure out what this diagonal, I'm going to call it D, was equal to, I would do leg squared plus leg squared is equal to the diagonal squared. So this is 25 plus 25 is equal to the diagonal squared. That's 50 is equal to D squared. Again, I'm going to square root both sides to get rid of the squared, and D is equal to the square root of 50. Again, I don't need the plus or minus because I don't need the negative value of it, given that I'm doing a length. So if I break this down, that's like 5 and 10. This is 5 and 2, so I have a group of 5s. So the diagonal is actually equal to 5 square root of 2. So I'm going to write this up here, 5 square root of 2. Notice in my next one, if I want to create a 45, 45, I go from corner to corner, and this again creates a right triangle where this is 45 degrees. If that one's 45 degrees, I know the other one has to be 45 degrees. And if I want to find the length of its diagonal, now that I've created this triangle here, I go ahead and do 10 squared plus 10 squared is equal to the diagonal squared. That's 100 plus 100, which is 200 equal to D squared, and I go ahead and square root both sides. D is equal to, again, I'm going to break this down, that would be like 20 times 10. That's 2 times 10, and I could keep going, or I have a group of 10s there, so this is like 10 square root of 2. So if I come up here and write this in, that becomes 10 square root of 2. You'll notice, again, this relationship here. The side lengths of my triangle are exactly the same, 5 and 5, and notice that the diagonal here is 5, or in other words, the side length times the square root of 2. It's square root 2 bigger. Here, my side lengths were 10 and 10. The diagonal here is 10 times the square root of 2. So it's always the side length times the square root of 2 bigger. Using that relationship on this last one, if I go ahead and draw in this diagonal from here to here, again, that creates a nice 45, 45 triangle, and we know this is, oh, I wrote 40, 90 degrees. And I know that this diagonal length here is going to be the side length, but times the square root of 2. It's the square root of 2 bigger than these two leg lengths. So anytime we're using this, right, if it's a 45, 45, this is how we write it, 45, 45 degree 90, then we have a triangle that is just half of a square. Okay, that is a nice triangle. I'm going to label this so we know that's what it's supposed to be. The legs are always the same length. So if this is length X, this guy's also length X. Those two are always going to be the same length on a 45, 45. And then again, the hypotenuse would be that length, but root 2 bigger, so times the square root of 2. Okay. That's the first relationship. And then the second one here is our 30, 60, 90. This one's built out of an equilateral triangle. So again, remember, an equilateral triangle, all the side lengths are equal in length, and because they're all equal in length, the angles are also equal. So if I take 3 angles, right, triangles sum up to 180 degrees. These 3 angles, I would just take 180 degrees and divide it by 3. They end up being 60 degrees each. So these are each 60 degrees in an equilateral triangle. And if I drop what we call an altitude down the middle, because all of the sides are equal in length, when I drop this straight down, okay, pretend that's in the middle, which it probably straightened it out for me. That creates a 90-degree angle down there. Notice that I've just created 2 triangles. I created one here on the left. There's a triangle, a right triangle, and here's one on the right. So we could look at either one. Let's look at the one on the right. So again, I'm going to kind of ignore the one on the left, but here's a leg of the triangle. Here's another leg of the triangle at the bottom, and then here is the hypotenuse of my triangle. When I drop that, because this is an equilateral triangle, it actually cuts that top angle in half, creating a 30-degree angle in my triangle. So now I've created a 30, 60, 90-degree triangle. So let's look at the relationship between its sides. Now I didn't give us an actual measure, so I'm going to, just to help us kind of look at it in the way we looked at the last one. Let's say that this is 6 centimeters long, which means that this is 6 centimeters long. And when I dropped that altitude, I actually cut that in half down there. So if this side is, or if it's 6 centimeters total, then each of the sides are going to be 3 centimeters. So I'm going to label that there. So in a 30, 60, 90, we have what we call the short leg, and we have the longer leg. The short leg is always opposite the smaller angle, so the 30-degree angle. And you'll notice, because it's an equilateral triangle, where we have a short leg and the hypotenuse, right, that come from those equilateral sides, the hypotenuse is always twice as big as the short leg. Okay, so just using that idea first before I talk about the other leg. Again, if I were to draw an altitude down here in the middle, pretend that cuts it in half because my drawings are definitely not equilateral. If these side lengths are, let's say, 4 centimeters, and again, when I cut that in half, I get 2 centimeters, 2 centimeters. This side right here, again, has become a 30, 60, 90. And you'll notice that that relationship there is going to hold. So again, if I know the hypotenuse right here is 4 centimeters, then that short leg is half of that. So that's the first one that we would look at. So what about the long leg? Let's talk about how that relates. Again, I'm going to use the Pythagorean theorem here on my first triangle. And I'm going to find, and I'll call this h so that it's not the same as the d. H for like the height. So if I use this triangle, I do h squared, because that's a leg, plus leg squared is equal to 6 squared. There's my hypotenuse. That's h squared plus 9 is equal to 36. Subtract the 9 over, and h squared is equal to 27. Square root both sides. H is equal to, let's break down 27. as much as we can. We've got a group of 3's there, so we get square root of 3. So up here, if I go to write this in, the height, or the long leg, is 3 square root of 3. Okay, now let's do one more so we can kind of see the pattern a little better. So here's my h. Again, I'm going to do h squared plus the little leg down here is 2 squared equal to, again, your hypotenuse squared, which is 4 in this case. So h squared plus 4 is equal to 16. Subtract the 4, h squared is equal to 12. Square root both sides, h is equal to, let's break that down to 3 and 4, 2 and 2, 2 square root of 3. So here we get 2 square root of 3. So notice on a 30, 60, 90 triangle, if you're looking at the height or the long leg, it's related to that short leg as well. Notice it's just the short leg times the square root of 3. Here it's the short leg times the square root of 3. So if I were to tell you over here that this was 2 centimeters, again, not drawn to scale, sorry about that, we would draw the altitude here. Oh, that's terrible. And here's a 30, 60, 90. If I label it, then it's okay. It's not drawn to scale, I guess. And we know, again, if that's 2 centimeters over here, we know that this little short leg is 1 centimeter. It's going to be half of the hypotenuse. And then again, we know that this long leg is just the short leg times square root 3. So this would be like 1 times the square root of 3 would be the length of that leg. So without having to do all the calculation, we can tell what that's going to be. So again, this one's called a 30, 60, 90 triangle. And I'm going to just draw a little diagram of one here. We have the short leg that's across from the 30 degrees. And I always use the short leg as the reference because if you know the short leg, so let's say that the short leg is given and the short leg is the value x, well, that's great because the hypotenuse is always just twice as big. So that would just be 2 times whatever x is. Okay? And then to find the long leg, we just know that it's square root 3 bigger than the short leg. So we just do x times square root of 3. So we've got like those two relationships. And let's see if it'll allow me to actually drag this. I don't know if it will, but let's move this to the next page. Oh, that's it. It was a good try. Okay, on to the next page. Let's just do a couple examples really quickly. So I'm going to draw them both out really quick one more time. So the 45, 45, 90. Okay, remember the legs are the same because it's half of a square and the hypotenuse is root 2 bigger. The other one is a 30, 60, 90. So this one, and we can draw either direction. Maybe I'll draw it the other direction just to kind of show you. We have the 30-degree angle, and then we have our shorter leg. And if that's x, then the longer leg is just root 3 bigger, and the hypotenuse is twice as big. So if we're looking at these two relationships, let's just do a couple examples. I'm going to draw some here. Let's say that we're given this figure right here. And we're told that this is 90, this is 45, and we're asked to find x and y, and we're given that this piece over here is 7, or this leg. The first thing I would do is recognize here's 2 legs, and it's a 45, 45. So in a 45, 45, I know that's half of a square, the legs are the same. So without calculating, I know that x is equal to 7, has to be the same as the other leg. Then I want to find the y value. Well, if I know the leg, again looking up here, the hypotenuse is just root 2 bigger. So I know it's going to be 7 square root of 2. Now, if I just have this picture right here, oh, I apologize, this picture right here, and I don't know that this is equal to 7 yet, so let's say I just wanted to find x, y. This we really can't do unless we know that this creates a 45, 45, and those are equal. Once you know this is 7 and this is 7, then I guess you could use the Pythagorean theorem to find the y value if you didn't remember the relationship. Okay, so there's an example. Another example with your 30, 60, 90. So let's draw one of those. And again, I'm going to lay it down just so it looks a little bit different. I'm given this is 30 degrees. And let's say we're given that the hypotenuse is 16. If this is the one that we're given and we've got x and y to find, Again, we want to recognize, well, it gave me the hypotenuse, so how are the other two related to the hypotenuse? Notice up here, the hypotenuse is 2 times x. It's twice as big as the short leg. It's a little bit harder to go from the hypotenuse to this one, so usually we go through the short leg. So if this is a certain value, I'm going to take half of that to find the short leg. So half of 16 is going to be 8. So I know that the short leg, right, across from the 30-degree angle, is going to be 8. Once I know the short leg, remember that the short leg relates to the long leg. It's just root 3 times larger, that long leg. So I take this, and this would be equal to 8, but square root of 3. Okay. I'm going to do one more of those, so I'm going to turn this the other way, but again, here's my 30-degree angle. And let's say that we're given this as 5. Okay. So again, the first thing I do is I look at what it gives me. Well, it just gave me the short leg. So in this case, what I'm going to do is I'm going to say, well, the short leg is related to the hypotenuse because the hypotenuse is just double that. So I know this would be 10, and I know that the long leg is just the short leg times the square root of 3. Okay, those are the easy directions. Let me do one more direction. So let's say I have this one right here, and this is my right angle, and this is 30 degrees. Now, it may tell you the other one's 60 degrees. Just recognize you always want to figure out which one's across from 30 degrees, so that's my short leg. On this one, let's say it gives me that the long leg is 10. Now, the tricky thing about it is it's not 10 times the square root of 3, so I can't just say, well, this short leg is 10, this leg is 20, twice as big. But remember, the short leg is related to the long leg. The long leg is root 3 bigger. So if you know it's root 3 bigger and you want to go backwards, you have to divide by the square root of 3. So I'm going to call this x and this y just to keep me not confused. So again, if I want to go backwards to the short leg, I need to divide by the square root of 3. So x is going to be equal to, right, this x down here is actually 10 divided by the square root of 3. Now usually we don't leave radicals in the bottom, so when we write this, we would multiply by the square root of 3. And we would end up with 10 square root of 3 over square root of 3 times square root of 3, which is the square root of 9, or in other words, just 3. So your value here, or the short leg, as weird as that looks, is 10 square root of 3 over 3. Now remember, once you know that leg, the short leg, then the hypotenuse is just twice as big. So you're just going to take 10 square root of 3. Oh, my pen seems to be not working, I apologize. But you're just going to take 10 square root of 3 over 3, and you're going to go ahead and multiply it by 2 or double it. So I was going to try and show you what that looked like. Oh, sorry. If we times that by 2, really that just multiplies the 10 by 2. So y would be equal to 20 square root of 3 over 3. Okay. Again, the relationships stay the same, maybe just the way that we write our answers a little bit messier. One last one, let's do with a 45-45. So again, this one can look a little bit messy just in relation to how that last one looked. So if I'm told this is 45 degrees, and let's say again we're told maybe this is 12, and I want to find x and y, I know, first of all, that this is a 45-45, so x and y are going to be the same thing, but I need to calculate it. Now normally when I know the leg, I just multiply it by the square root of 2 to find the hypotenuse. In this case, you know the hypotenuse, so you got to go backwards. You're going to divide it by the square root of 2. So to find x or y, either one, I'm going to do 12 divided by the square root of 2. Again, we don't like radicals left in our denominator, so we go ahead and multiply that by square root of 2. We get 12 square root of 2 over square root of 2 times square root of 2 is the square root of 4, which is 2. And then if I simplify that 12 and that 2, I end up with 6 square root of 2 as my x value. And then I know that the y value is the same thing, so 6 square root of 2. Okay. Last one, if it gives it to you, let's say it gave it to me in, and I'll just show you kind of using the same one, if this is 45 degrees, and it told me that this leg is 6 square root of 2, and this is x, and this is z. I don't know, we'll use a different letter. Again, I would know that the legs are the same length, so x would be equal to 6 square root of 2. And then remember, z is square root 2 bigger. So if I wanted to find z, I would take 6 square root of 2 and multiply it by square root of 2 because it's going towards the hypotenuse. So z would be equal to 6 square root of 4. Or in other words, right, that's just 2. So z is equal to 12. So you can see how it will go both directions, whether I know this is 12 and I'm headed back to the legs, or if I know the leg and I'm headed to the hypotenuse. Okay. Again, your goal today is to be able to, first of all, understand where they come from so that you can recognize why these legs are always the same, why the short leg is half of the hypotenuse on a 30, 60, 90, and then practice using them. The more you practice using these, the easier they become to remember and to relate them together.